This Zoom session is being brought to you by the Fractal Thin Dragon. All right, today we end up chapter 7 with complex numbers and begin chapter 8 with solving quadratics. Okay, complex numbers. Basically, well, complex numbers is the end, one of the stops in a sequence of mathematical innovations. We started off with counting numbers, 1, 2, 3, 4, 5, and so on. And even there, we had to invent a zero number just to be able to write arbitrarily large numbers. Then you invent negative numbers and zero. Then you invent fractions, and then irrationals. And now we want to solve this equation: I squared equals -1, for reasons that will be useful later to solve quadratics and ultimately cubics and others. The problem is that if a positive number squared is positive, 0 squared is 0, and a negative number squared is positive. So none of them square to a -1. Now, you can give this solution a name called the square root of -1, called I, but it has to be neither positive 0 nor negative. So it's not on the real number line, and that's why it's called the imaginary unit. This is something happens often in math. They come up with something which they can't quite figure out yet, and so they give it a scary name. Imaginary, irrational. All right, fine. Well, okay, since there's nowhere on the real line, well, it has to be off the real line. And in fact, we consider it as a kind of sideways unit. So instead of being to the right or to the left, like the positives or the negatives, it's off at 90 degrees. And so what we're dealing here with a two-dimensional number system. So a complex number, therefore, is in the form a plus I times b, where b is the square root of -1. It's located in the complex plane over left, right, a distance a, up, down, a distance b. So here's a plus ib. This is like rectangular coordinates. So basically, these are rectangular coordinates, only we'll be able to do arithmetic with them. We'll add, subtract, multiply, and divide. All right, a plus ib. A is called the real part. B is called the imaginary part. Now, we can define arithmetic on these numbers. Oh, they're called C, the complex numbers. This is another time where they give it that thing they didn't really understand at the time, a scary name. Complex meaning made of two parts. It's not more complicated than what are called the real numbers, which is an exaggerated name too. I actually prefer to call them the plane numbers. Anyhow, we can define plus, minus, times, divide on them by geometry and by arithmetic. Very useful thing. Okay, so here is adding complex numbers. If you have two complex numbers, a plus ib and c plus id, you add the real parts, a plus c, and you add the imaginary parts, b plus d. We're adding these two parts in parallel. This is basically as if you're using the usual laws, associativity, distribution, and commutativity. Just operate as if these numbers were acting like the ones you already know. So this follows. Now, the geometry of it is that if you have the complex plane, and here's the number 0, and here's the number z, and here's the number w, you draw this line here, and draw this line here from 0 to z and from 0 to w. Then you draw this line here parallel in the same length as this. Draw this line here parallel in the same length as this. So you get a parallelogram. And this far corner is z plus w. Now, to subtract complex numbers, well, you subtract the real and imaginary parts separately. A plus ib minus c plus id. The real part is a minus c. The imaginary part is I times b minus b. Here. Another way to think of it is if you want to find z minus w, and here's 0, and here's z, and here's w. Well, if this is w, then minus w points in the same length in the opposite direction. Then you add z and w by the parallelogram rule, and here it is, z minus w. Notice that it forms a kind of letter D for difference. Now, to define multiplication in the complex numbers, you use FOIL, assuming that these FOIL works, assume that works for these numbers as it does for ordinary real numbers. Use FOIL, and also the rule that I squared equals -1. This is where the peculiarity of the complex numbers come in. So you have A plus IB times C plus ID. First is AC, outer is A times ID, inner is I times BC, and last is I squared BD. Now okay, AC plus I squared BD here. These have a factor of I in common. You pull it out. I times AD plus BC. And since I squared is -1, this really becomes AC minus BD. That plus I times AD plus BC. So this is a formula for complex multiplication, and it's sort of tiresome to memorize. So you might as well just use FOIL and I squared equals -1. So for example, 5 plus I times 3 plus I times 2. Oh, by the way, the book likes to use A plus BI. I prefer to use A plus IB, putting I in front, like it's a sign, like plus or minus. I is basically the sideways unit. All right, so multiplying it out, 5 times 3. Oh, then I3 times I2 is -3 times 2. And I times 3 squared, and I times 5 times 2. So it'll be 15 minus 6 plus I times 10 plus 9. Therefore, 9 plus 9, I19. And here we have 5 plus I times 3 times 5 minus I times 3. This is a difference, a sum times a difference, which you may recall is a difference of squares. And if we expand it out, 5 times 5 here, minus 3 times -3 here, I times 5 times 3 times 5, minus I times 5 plus 3, 5 times 3. All right, so this is 25 plus 9. This is 15 minus 15. This, the imaginary part, cancels. And we're left with a purely real number, 34. Now, so okay, this number, I plus I, 5 plus I3, 5 minus I3, these are called conjugates. And when you multiply a conjugate, you get a real number. Let's see that in general. We mentioned that in the next page. Yes. A plus IB times A minus IB. These are called conjugate numbers. And their product is A squared plus B squared, because it's A squared minus IB squared. But I squared is negative, so it cancels, and you get a plus B squared. You recall I said earlier how a difference of squares factors into A minus B times A plus B. I said we couldn't quite yet factor a sum of squares. This is how you do it. Now, for example, 3 plus 4i times 3 minus 4i. Oh, I used the other notation. Okay, it'll be 3 squared plus 4 squared. That's 9 plus 16, or 25. 7 minus 2i times 7 plus 2i. That'll be a sum of squares. 7 squared plus 2 squared. That's 49 plus 4 is 53. Okay. Now, we can use this to divide complex numbers. I mean, we've seen before rationalizing denominators with square roots in it. We'll do the same thing. 1 over 3 plus 4i, what's that? We'll take 1 over 3 plus 4i and rescale by the conjugate of the denominator. The denominator is 3 plus 4i, the conjugate is 3 minus 4i. So multiply above and below by 3 minus 4i. 1 times 3 minus 4i is 3 minus 4i. 3 plus 4i times 3 minus 4i is 25. 3 squared plus 4 squared is 25. Then break this into two parts. 3 25ths minus I times 4 25ths. That is the reciprocal. 1 over 3 plus 4i. Now here we have a ratio. 1 plus 3i over 7 minus 2i. This again we rescale by the conjugate of the denominator. 1 plus 3i over 7 minus 2i. The conjugate of 7 minus 2i is 7 plus 2i. I always switch the sign of the imaginary part. So 7 plus 2i, 7 plus 2i. Multiply across and we get the usual stuff. Okay, 1 times 7 minus 3 times 2, that's 7 minus 6. 3 times 7 plus 1 times 2, that's 21 plus 2. Here we have 7 minus 2i times 7 plus 2i. That's equal to a sum of squares, 7 squared. plus 2 squared, that's 49 plus 4. Now a bit of cleanup. 7 minus 6 is 1, 21 plus 2 is 23, 49 plus 4 is 53. Then we'll distribute the 53 underneath these two terms. So 1/53 plus I times 23/53. Okay, so let's do some arithmetic. We add some complex numbers, here we subtract them, we multiply them, here we square one. Well, that's the number times itself. Here we go. 6 minus I plus 9 plus 3I. The real parts are 6 plus 9. The imaginary part is minus 1 plus 3. This is 15, this is 2, so 15 plus I times 2. 7 minus 3I minus 4 plus 2I. Well, the real part is 7 minus 4 here. The imaginary part is I times negative 3 minus 2 here. So that comes to 3 minus I times 5. Here is 2 plus I times 3 minus I. 2 times 3 here, minus 1 times negative 1, that's here. Then plus 3I minus 2I, that's here. This is 6 minus plus 1 plus I times 1 is 7 plus I. The square of 2 plus I, well, that's 2 plus I times 2 plus I. And now, 2 times 2, that's here, minus I times I, minus 1. I times I is minus 1. Then 2I plus 2I, that's 2 plus 2 times I. This comes out to, so this is 4 minus 1, that's 3, plus I times 4. All right, now you have some ratios of complex numbers and another square. I'll do the square first. 4 minus 8I squared. Okay. Well, okay, you can use a shortcut. A square of a difference is a squared minus 2ab plus b squared. That's 4 squared minus 2 times 4 times 8I plus 8I squared. That's 16 here. Minus 2 times 4 times 8I is minus 64I. 8I squared, 8 squared is 64, I squared is minus, so minus is 64. 16 minus 64I minus 64, these combine to minus 48 minus 64I. That's what this is. Now let's get to these. 3 minus 2I over 4 minus I. Take that and multiply, rescale, multiply above and below by the conjugate of 4 minus I. That's 4 plus I. 4 minus I times 4 plus I is the sum of squares. 4 squared plus 1 squared, which will get 16 plus 1, which will make it 17. In the numerator, 3 times 4 is 12. Minus 2 times I is minus a negative 2. Minus 2 times 4 is a minus 8. 3 times I is a 3i. So 12 minus negative 2 is a 14. 3 minus 8 is a negative 5. So 14 minus 5 I over 16 plus 1. So distribute the 17 underneath. 14 17ths minus I times 5 17ths. You have 5 plus 9I over 1 minus I. We'll take this and multiply above and below by 1 plus I, the conjugate of the denominator. 1 minus I times 1 plus I will be 1 squared plus 1 squared, which will be 2. And now this. 5 minus 9 here, 9I plus 5I here. So this, so 5 minus 9 over I times 5 plus 9 over 1 squared plus 1 squared. That's negative 4 from here plus I times 14 from here all over 2. And then you divide these both terms by 2 and you get negative 2 plus I times 7. There you have a pretty easy one. You have the square of 2I, you have the square of 2 plus I. Square of 2I, you distribute the square, 2 squared times I squared, that's 4, that's a negative 1, so the product is negative 4. plus I squared, the square of a sum is square plus twice product plus square. So 2 squared plus 2 times I plus I squared. This is 4. This is 4I. This is minus 1. And so you get combining terms 3 plus 4I. Now you may be asking, why do we even have this complex number? Well, okay, later we'll see it fairly soon. We'll be seeing that it solves general quadratics. Sometimes a quadratic has no real solutions, but it'll have two complex solutions. The real reason, actually, the one that really works, is that well, we'll see later, I think, that complex numbers are really an arithmetic of rotations, because that I is basically a 90-degree rotation. A complex number is a length and a rotation. So multiplying is sort of like involves rotations, and this means that it's a natural arithmetic for cycles. Now it turns out that maybe you've heard of Tesla, Nikola Tesla. He had a big argument with Thomas Edison, who swindled him, by the way, about whether or not to use direct current or alternating current for electrical transmission. Ultimately, Tesla won, and we have alternating current for electrical transmission because you can send it further a lot cheaper and so on, and it's easy to make motors out of it and so on and so forth, just stuff. But it turns out that the equations that describe alternating currents are the same as the equations describing direct currents, only allow complex numbers for resistances, voltages, and currents. Keep that. All right, enough of that. All right, that ends this part of it.